What's going on, smart people? Finally bringing you another episode of Tensor Calculus for Physics. In this video, we're going to be deriving the expressions for divergence and the Laplacian in tensor notation. And I'm excited for this video because we've done all of the heavy lifting we need. We know how to make sure we're working with tensors, and when we differentiate them, how to retain that tensor structure. Namely, in previous videos, we defined the covariant derivative, which was the modified version of the derivative, such that when we took derivatives of tensors, the end result was still a tensor. And now we can just reap the benefits of that. We don't have to reinvent the wheel every time we work with a different differential operator. Now, to give you a bit of a timeline for this video, well, first and foremost, when we differentiate vectors here, we're talking about covariant or contravariant vectors, which are different but related to the ordinary vectors that you'd see in, say, Griffiths. So to start off, we're going to start off with a refresher on how all of those things are related. That way, when we derive our expression for the divergence, we can compare apples with apples. Then we're going to jump right into deriving the expression for the divergence in tensor notation. We're going to do an example where we just recover the divergence in spherical coordinates. And then finally, we are going to just simply write down the expression for the Laplacian in tensor notation. And we can do that because once we have divergence in tensor notation, the Laplacian is just the divergence of the gradient, so it'll just be a one-liner. Okay, as one disclaimer though, there will be one step in the simplification process that I kind of skip over because I'm saving it for a future video. One, it would almost probably double the length of this video, which is fine, but it's got more application than just in deriving the divergence, so anyone else looking for that derivation or that step probably wouldn't be looking for it in a divergence video, so I hope you'll forgive me there. So first and foremost, let's do our little crash course on covariant, contravariant, ordinary vector stuff. I do have an entire video on it, link in the description. But it all started with saying we want to take a look at an infinitesimal line element ds squared, and then Cartesian coordinates, that would just be dx squared plus dy squared plus dz squared. And I can write this where I have some dxi is a vector. I'm going to put a little tilde on it. So this is my ordinary vector. Ith component is my dx, dy, dz. Okay, so this is like my displacement vector that you would work with in say, any other physics course. We can also write this in spherical coordinates as the following. It would be equal to dr squared plus r squared d theta squared plus r squared sine squared theta. Yeah, that's right, sine squared theta d phi squared. In which case dx tilde I would equal dr r d theta and r sine theta d phi. So those are the displacement vector in a different coordinate system. Now the big punchline of that video where we were distinguishing the different vectors is that coordinate displacements do not always have units of distance. Right? In this case, if we're in Cartesian coordinates, dx, dy, dz, those all have units of distance, they have units of length. Dr has units of length, but d theta does not. However, every element of the displacement vector is a distance. R d theta is a distance. R sine theta d phi is a distance. So what we started looking for was an object that was able to convert these coordinate displacements into distances, and that was the fundamental role of the metric tensor. So that we were able to write this ds squared in tensor notation by incorporating the metric tensor. It's called g mu nu. Actually, I'm using Latin index, so let me just use gij for here. Gij dxi dxj, where the superscripts now were defining what was called the contravariant vector, the contravariant displacement vector. So dxi without the tilde, as the superscript, would be, well, it would still be your dx, dy, dz, because those are your coordinate displacements in Cartesian coordinates. However, in spherical coordinates, it would just be your dr, d theta, and d phi, your coordinate displacements. So when we act on these objects with the metric tensor, it knows when to tack on units of distance when it needs to, and it leaves it alone otherwise. So in spherical coordinates, we would have that the metric tensor is equal to 1 r squared sine squared theta, with zeros as the off diagonal. So when we have a product of dr times dr, so that's I equal to j, that's the first element, that would just multiply it with a 1. That would give us a dr squared. And then if we had d theta, those don't have units, that would be multiplied by an r squared here. And then the same goes for the d phi squared. Awesome. And then the off diagonals are because we don't have mixed terms like dr d phi or something like that. Okay, so we see that there's this difference between the coordinate displacement vector and the ordinary displacement vector. And how can we express this relationship? Well, we said that this metric tensor is diagonal, so we can write it as a product of coefficients with the Kronecker delta. So we can say, we'll call it hi, let's say gij is equal to some coefficient hi times the Kronecker delta, delta ij. This should not be a mixed tensor. And here, there's no sum implied. So I is equal to j, so h1 would be 1, h2 would be r, and h3 would be r sine theta. And actually, this should be squared, right? So if we're squaring this, then h1 would be 1, h2 would be r, h3 would be r sine theta. Okay, but look at how these displacement vectors are related to the contravariant vector. So this dxi is like our prototype for the contravariant vector. Any vector that is derived from a coordinate displacement in the numerator, I would say, is an example of a contravariant vector. So if we look at, say, the second element here, we have a r d theta. Here there's no d theta. That's the same as saying that dxi, the contravariant vector, is the regular vector, or the ordinary vector, dxi tilde divided by hi. Divided by that scaling factor that converts everything to a distance. Okay, but we still want to be able to take dot products, scalar products between contravariant vectors and whatever need be, so that we get that the dot product reduces to just dx tilde dot dx tilde. So we define what's called the covariant vector, dx lowercase I, which would be hi times dx tilde I. Again, with no sum over anything here. Okay, so this defines our contravariant and our covariant vector. Contravariant because as hi gets larger, the length of our contravariant vector gets smaller, and the opposite happens with our covariant. As h gets larger, dxi gets larger. It varies with it. Okay, awesome. So that is our relationship between contravariant, covariant, and ordinary vectors. And now if we want to write down something like an arbitrary vector, we have, and I'm going to switch over to Greek indices now. If I have some vector a mu, it's related to the ordinary vector a tilde mu over h mu, and a mu is equal to h mu times a tilde. Okay. So if you take derivatives of coordinate displacement with respect to a scalar, however many times, that would be an example of a contravariant vector. If you're taking derivatives with respect to coordinate displacements, that would be an example of a covariant vector. That was our prototype, was the gradient, in a sense. So if we look at this covariant relationship here, if we have a derivative with respect to a coordinate displacement acting on a scalar function f, that would be equal to, well, that would be equal to what? That would be equal to h mu times the ordinary one. But the ordinary one would be a derivative with respect to a distance. That's exactly the gradient. Okay, so we have the gradient of mu. Let's see if we can connect that dot a little bit better. F. Okay. So here this just gives us our relationship between derivatives with respect to coordinates and derivatives with respect to distances. Okay. Okay, so now we can finally move on to the covariant stuff. if we're working with a scalar function, so first of all, let's write down the definition of the covariant derivative of, say, a vector function. D mu, let's say, a lambda. That would be equal to the derivative with respect to mu of a lambda plus a linear transformation on the vector a. A mu nu, a nu. In flat space, this is saying that we're taking the derivative. It could be the vector itself that's changing, which is what we're taking the derivative of, plus the possibility that the basis vectors themselves are changing when we take this derivative. Like if you're confined to a circle, then your phi hat, the direction is actually changing as you go along the circle. So these Christoffel symbols, these connection coefficients, are serving the role of characterizing the fact that the basis vectors may be changing as well. You can't really think of it quite like that in curved space, but for this, that's good. If we're taking the derivative of a scalar function, we're not characterizing that with basis vectors. It's a scalar, so there's no need to do that. In other words, the covariant derivative of a scalar function just becomes this guy here anyways. We don't need to add connection coefficients. As a general rule of thumb, you need one set of connection coefficients per index of the object that you're differentiating. Okay, so this was our covariant derivative of a vector. Now we want to take the covariant divergence. So that's just the dot product of the covariant derivative with the vector. So let's see. Let's erase this real quick, and what I want to write out is I'm going to substitute this a lambda for an a mu. A mu. So this would be the notation for the covariant divergence. D mu a nu, or a mu, plus gamma mu mu, and let's say lambda here. Okay. Okay. So we need to sum over lambda, and then mu index has to be summed over as well, so we have a repeated mu in the connection coefficients. And luckily, I have already taken the liberty of writing down what those connection coefficients are in general. So let's go ahead and copy those and drag them over. So let's drag this guy down here. And what we want to is we want to simplify this gamma mu mu lambda, or we want to simplify the recall expression into the gamma mu mu lambda. So then gamma mu mu lambda would be equal to 1/2 g. So let's see. Up here we have a lambda, here we have a mu, so we're replacing this lambda with a mu. Okay. D mu g. So nu was on the right hand side, so that's going to be a lambda. So lambda k plus d lambda g mu k minus dk g mu lambda. Okay. Now let's see if we can simplify this a little bit. So the first term, we're raising both k and mu. So we're raising this d mu here, and we're raising this dk here. And then the metric tensor is a symmetric tensor, so we can swap indices. Now not only that, but we're summing over these variables, or we're summing over k, so we can write this, let's say, what do I want to write here? Lambda's not being summed over, so I could write this guy as d mu gk lambda, since the metric is symmetric. And we're summing over k, so we can rename that k variable to match this mu variable here. And what I'm getting at is that these two terms cancel. Right? The metric is symmetric, and we're summing over those two variables, so these are the same term, and they cancel. So these connection coefficients simplify, and it just becomes a 1/2 g mu k d lambda g mu k. And here comes the step that I said that I'm skipping. This was equal to this step, and I'm saving it for another video. This expression can be expressed, so we can simplify gamma mu mu lambda equal to a 1 over the square root of the determinant of g the derivative with respect to the lambdath coordinate of root g. So this step here we're going to prove in a different video. And the reason for that is because derivatives of things like the of determinants of the metric show up in more places than just this. As an example, the energy momentum tensor T mu nu in general relativity is proportional to the variation of the action with respect to the metric tensor. And the action is the integral over four-dimensional coordinates. And then we have this root minus g in the integration measure, which serves the role of our Jacobian. And then we have the Lagrangian density that we're integrating over, and we're taking the derivative with respect to the metric here. So to find the energy momentum tensor, we have to take this derivative of the determinant of the metric with respect to the metric components, which is, there's a kind of a trick to it, with like exponentials of determinants being related to exponentials of traces and things. So that step is just bigger than just this video, so I'll save it for another video, and I hope you don't mind. But for now, let's just, you can take my word for it, or you can, maybe that's something you might want to look into for yourself before I make the video on it. So we're just going to use this expression here, and we're going to substitute it into our definition for the covariant divergence. Covariant divergence then becomes d mu, a mu, is equal to d mu, a mu, plus 1 over root g d lambda root g a lambda. Now we're summing over lambda. That's a dummy variable. From the beginning of this series we saw, like, I understand that it's confusing when you can relabel indices. You can always relabel an index if it's being summed over. So I'm going to relabel this lambda to a mu. Right? There's no lambda dependence. There's no mu dependence on this stuff either because we're summing over it. We can name it whatever we want. So I'm going to relabel a lambda to a mu, or these lambdas to mu's. Okay. Well, if I factor out this 1 over root g, 1 over root g, so this would be a root g d mu a mu plus d mu acting on just root g a mu. We can combine these terms with product rule. This is just, this guy here is just d mu of root g a mu. Right? Using product rule, you differentiate the determinant of the metric, that's this guy, and then don't differentiate a mu, and then plus don't differentiate the determinant times the derivative of a mu, that's this guy. Okay? So our final expression for the covariant divergence can be expressed d mu a mu is equal to 1 over root g d mu root g a mu. There we have it. That's the covariant divergence. And I didn't specify it in this video. This root g is equal to the root of the determinant of the metric. And in principle, you'll have, for spaces where that determinant is negative, you'll see a little absolute value here. So it's like the absolute value of the determinant of the metric g. I think I've specified that in a previous video, but just for completeness. Cool, so that's it. That's the expression for the covariant divergence. Now we can just work on making sure that it's consistent with what you've seen in the front of Griffiths or something. One comment that I do want to make before we do that, if we take a look at this term here, this is a derivative with respect to a coordinate of the vector. Derivatives with respect to coordinates do not necessarily have units of 1 over distance, as we've shown. So there needs to be some simplifying in order to make sure that when we take divergences, it has the same units as what you would look up in Griffiths. And that's going to happen by replacing this a mu with the ordinary vector, with how they're related. So in the top, we have the a mu contravariant, which is the regular vector divided by this coefficient that might have units of distance. So that's where it's going to come from. Just a little spoiler. Okay, now let's go ahead and do an example where we derive the divergence in spherical coordinates. So example, spherical. Okay, in flat space. Okay, let's just go ahead and jump right into it. So the first thing is that the metric tensor g mu nu is 1 r squared sine squared theta, which means that the square root of the determinant of g, the determinant of a diagonal matrix is just the product of the diagonal components. So we're taking the square root of the product of the diagonal components. So that's square root of r squared times r squared sine squared theta. So that's the square root of r squared sine r to the fourth sine squared theta, which is equal to r squared sine theta. And lo and behold, wow, that's why you see in doing any integral in spherical coordinates, there's that r squared sine theta dr d theta d phi. It comes from this Jacobian factor. Okay, now let's just do our plug and chug. So d mu a mu is then equal to 1 over r squared sine theta d over, now we're just going to sum over the index, d over dr root g, so that's r squared sine theta a upper r plus d over d theta r squared sine theta a theta plus d over d phi r squared sine theta a phi. Now let's make the substitution of how these contravariant vectors are related to the ordinary vectors. So we just divide by that h that corresponds to that element of the metric. So that's going to be equal to 1 over r squared sine theta d over dr r squared sine theta ar tilde divided by 1, right? So we're dividing by effectively the square root of whatever element that corresponds to in the metric, plus d over d theta r squared sine theta a theta tilde divided by the square root of r squared, so that's r, d over d phi r squared sine theta a phi tilde divided by r sine theta. Okay, getting a little messy, but it'll simplify, the dust will settle. So this is equal to 1 over r squared sine theta so this whole thing will simplify into, and the sine of theta cancels in the first term, so this becomes a 1 over r squared d over dr of r squared a sub r tilde plus, so this one of these r's cancels, so we get a 1 over r sine theta d over d theta of sine theta a theta tilde plus a 1 over r sine theta d a phi, sorry, they should have a tilde, d phi. And there is our expression for the divergence in spherical coordinates, just like what you would see in Griffiths. Now, if you're observant, you may notice or you may question one of the steps that I did, and I had the exact same question. we go through all this trouble of relating a mu to the vector in like the ordinary vector. Why don't we also do that for the d mu? The d mu is the covariant vector. Why don't we try to relate that to the regular gradient operator, the nabla operator? The reason for that is because if we look up here, this guy has units of 1 over coordinate displacement, whatever that may be. If we want to relate this d mu to the gradient, we have to divide by the h mu. Well, how do we get that factor of 1 over h mu? Well, we get that by replacing the a mu with the ordinary vector, which is going to be the a tilde divided by h mu. So in replacing the a mu with a tilde over a mu over h mu, this d mu acquires the 1 over h mu it needs in order to be related to the gradient. If I'm speaking gibberish right now, let me just point to it up here. Whoops. The d mu is related to the gradient by dividing by this h mu. So if we want to be able to compare, if we want to compare this d mu to the gradient, we need to get a 1 over h mu from somewhere, but we get that exactly from the h mu that we're working with. We get that 1 over h mu for free. And that will happen every single time because we need to preserve the form of the scalar product. If we're writing things in terms of a tildes, a tilde dot a tilde should give us our scalar product. So if we replace one of these guys with something in terms of a tilde, the other guy should be equal and oppositely compensated so that we're preserving the scalar product. So that's why we didn't consciously have to do anything with the d mu. It took care of it for us. So that's the divergence in spherical coordinates. Now the last thing is we want to find out what the Laplacian is. The Laplacian of, say, let's write it out first. So usually we'd write that as del squared of a scalar function phi, which is just the divergence of the gradient of that function phi. Okay, well now we know the gradient of a scalar is just another vector. So really all we're doing here is we're taking the divergence of a vector. So if we write this in covariant form, we're replacing derivatives with covariant derivatives. So the covariant generalization is just d mu of phi. Okay, but the covariant derivative of a scalar function is just the regular derivative. So this is going to be equal to this expression that we derived. So I'm going to write out the divergence term. So that's that 1 over root g d mu root g. And then this is what was acting on, this whole term was acting on our vector, but now our vector is the gradient. So that's just going to be our d mu phi. That's our covariant vector. The contravariant vector, sorry. So we don't have to do anything anymore. That's actually it. That's the entirety of, we did the divergence, and then this gradient, well, contravariant version of the gradient of a vector, that's also going to be a vector. So we just have to use that as our vector in our divergence, which is just this guy. And again, you don't have to do any Christoffel symbol stuff because phi is a scalar function. So then this becomes immediately our Laplacian in tensor notation. 1 over root g, d mu root g, that comes from the divergence, acting on our vector, which is d mu phi. So that's our covariant Laplacian. I have a video going over the Laplacian as an example. I'll leave a link in the description. I think I do it in cylindrical coordinates because even though this is a simple equation, that doesn't change the fact that in spherical coordinates the Laplacian is still pretty gross. But in its essence, that's all there is to it. That is the divergence and the Laplacian in tensor notation. In the next video, I'll either do that proof that I mentioned, or I'll jump straight into curl, because that's the last thing that we need to go over. And then after that, we're starting to get right into the physics. We can start talking about curvature and inching towards the Einstein field equations. So I hope you guys enjoyed this video. Let me know in the comment section if you did, and I'll see you guys there.